what hydrostatics is, and how a fluid pushes. We are beginning hydrostatics, which is the part of fluid mechanics that studies fluids at rest. A fluid is anything that flows under an applied force, and that includes both liquids and gases. The defining property of a fluid is that it offers almost no resistance to a sideways push, which is why a fluid simply takes the shape of whatever you pour it into. To keep our language precise, we split fluid mechanics into two branches. Hydrostatics, which we are starting now, deals with the fluid when it is at rest. Hydrodynamics takes over once the fluid starts moving. In this deck, we are entirely on the hydrostatics side. When a stationary liquid presses on a surface, the total normal force it delivers is called the thrust, and thrust has a useful SI unit, the Newton. The next step is to spread that force over an area, and that gives us a new quantity, pressure. Pressure, thrust per unit area. Pressure is just thrust divided by area, so it is the normal force a liquid exerts per unit area of the surface it touches. We also call this hydrostatic pressure when it comes from the weight of the liquid alone. The defining formula is P equals F over A. Three things about that formula are worth holding on to. First, pressure is a scalar. At any point it has a single value with no preferred direction. Second, its SI unit is the Newton per square meter, which we call the Pascal, abbreviated Pa. Third, the dimensions of pressure are mass times length to the -1 times time to the -2. There is one extra result you should keep on the shelf for later. A column of liquid of height h sitting on a base exerts a pressure of h rho g on that base, where rho is the liquid's density and g is the acceleration due to gravity. The average pressure on the side wall of the same vessel is exactly half of that value, h rho g over 2. We will use the depth form over and over in this lesson. Pressure increases with depth. Now let the fluid settle. Take 2 points at depths separated by a vertical distance h, and ask how the pressure at the lower point is related to the pressure at the upper point. The liquid above presses down on the liquid below, so the deeper point has to carry the weight of the column between them. Write the free surface pressure as P sub A and write the vertical depth as h. Then the pressure at depth h is P equals P sub A plus h rho g. Each extra meter of fluid adds rho g pascals to the local pressure. The horizontal position of the point is irrelevant. The formula only cares about the vertical distance below the free surface. Keep that point in mind because the next big idea depends on it. Atmospheric pressure, the air above you. The atmosphere around us is itself a fluid and a tall one. It weighs down on every surface it touches, and that weight per unit area is atmospheric pressure. At sea level, this atmospheric column balances a column of mercury about 76 centimeters tall. In centimeter-gram-second units, the pressure is H times D times G, which works out to 76 times 13.6 times 980 dynes per square centimeter. In SI units, the same number becomes 0.76 times 13.6 times 10 to the 3 times 9.8 newtons per square meter, which is approximately 1.013 times 10 to the 5. So 1 atmosphere equals 1.013 times 10 to the 5 pascals. Two smaller units show up often in the lab. 1 torr equals 1 millimeter of mercury column, and 1 bar equals 10 to the 5 pascals, very close to 1 atmosphere. The atmosphere does not crush us because the fluids inside our bodies push back with the same pressure. A barometer that does not use liquid mercury is called an aneroid. Other common pressure gauges are the open-tube manometer, a tire gauge, and the cuff instrument used to measure blood pressure. Gauge pressure, what the instrument reads. Most gauges do not actually read absolute pressure. They read the pressure above local atmospheric pressure, and that excess is called the gauge pressure. In symbols, gauge pressure equals total pressure minus atmospheric pressure. A flat tire reads 0 on its gauge, but the air inside is still at 1 full atmosphere of absolute pressure. The depth formula uses the total pressure P sub A plus h rho g. The h rho g part is the contribution made by the liquid itself, and that is exactly what a gauge is designed to display. The hydrostatic paradox. 3 rules. The hydrostatic paradox captures the most counterintuitive consequence of the depth formula. The pressure at a point inside a liquid does not depend on how much liquid there is. It depends only on the depth below the free surface. 3 rules follow directly from the equation P equals P sub A plus h rho g. First, at any single point the pressure is the same in every direction. We call this isotropy at a point. Second, in a connected liquid, every point that sits at the same horizontal level carries the same pressure. Third, the shape of the containing vessel does not matter for the pressure at a given depth. 3 vessels filled to the same height produce the same pressure at the base. even when they hold very different masses of liquid. Same depth, different weights, and a floating block. Let us pin the paradox down with a picture. Take three vessels, a frustum wider at the bottom, a straight cylinder, and a cylinder with a U-shaped concave bottom. Fill each with the same liquid to the same height h, under the same atmospheric pressure P0. At the base the pressure is identical in all three. It is P0 plus rho gh. That is the same number for the frustum, the straight cylinder, and the U-bottom cylinder. What is not the same is the weight of liquid each vessel holds. The frustum, being widest at the base, holds the most liquid. The straight cylinder holds less. The U-bottom cylinder with its scooped-out base holds the least. The weights W sub x, W sub y, and W sub z decrease in that order. So the same base pressure, three different weights of fluid. That is the paradox in one image. Now drop a block of mass m on the free surface and let it float. The block's footprint is A, the liquid has density ρ, and it still stands at height h above the base. The pressure at the base now becomes P0 plus rho gh plus mg over A. Read the three terms from top to bottom. The atmosphere pushing down on the surface, the column of liquid itself, and finally the extra weight of the block spread over its footprint. This is the cleanest statement of the paradox. Pressure cares about depth, weight cares about the volume of fluid actually present. Transfer point: three things to carry forward from this deck. First, the pressure at depth h in any liquid open to the atmosphere is P equals P sub A plus h rho g. Second, that pressure depends only on depth and density. The shape of the vessel and the total volume of fluid are irrelevant at a point. Third, atmospheric pressure is about 1.013 times 10 to the 5 pascals, and that is the reference we subtract to get a gauge reading. With pressure locked in, the natural next question is what happens when a solid object sits inside this pressurized fluid. That is the topic of the next deck: buoyancy, Pascal's law, and Archimedes' principle. Buoyancy and why the fluid pushes up when a body is partly or fully immersed in a fluid. The fluid pushes it upward with a force we call buoyancy, and the force itself is the buoyant force. Its magnitude is F equals V rho g, where V is the volume of fluid that the body actually displaces. Rho is the fluid's density, and g is the acceleration due to gravity. The force acts at the center of gravity of the displaced fluid, a point we name the center of buoyancy. Why does the force point upward? Place a cube of side fully in the liquid with its top face at depth h. The pressure on the bottom face is h plus a times rho g, while the pressure on the top face is just h rho g. The side pressures cancel by symmetry. Take the difference, multiply by the area squared, and the net upward force works out to a cubed rho g, which equals V rho g. The pressure difference argument makes no use of the cube shape, so the same result F equals V rho g holds for any body, no matter how irregular. Pascal's law: pressure travels undiminished pascals. Law takes the hydrostatic pressure we just derived and turns it into a transmission rule. Any extra pressure you apply to an enclosed fluid at rest travels through that fluid equally and undiminished to every other part of the fluid and to the walls of the container. The practical consequences are mechanical. Press a small piston with a small force and the same pressure appears at a much larger piston where it produces a much larger force. That is the hydraulic lift, and it is how a garage jack hoists a car. Press the brake pedal in a car and equal pressure travels through the brake fluid to all four wheel cylinders, so hydraulic brakes are another direct application of Pascal's law. In symbols with input area A1, output area A2, and corresponding forces F1 and F2, F1 over A1 equals F2 over A2, which rearranges to F2 equals F1 times A2 over A1. The trade-off is distance. The small piston must travel a proportionally larger distance. Energy or work is conserved through the system. What is multiplied is force. Archimedes' principle states that when a body is partially or fully immersed in a liquid, it experiences an apparent loss of weight equal to the weight of the liquid displaced. Mathematically, this apparent weight is the real weight minus the buoyant force. If we define A as the loss of weight in water and B as the loss of weight in another liquid, their ratio A over B is equal to the weight in air minus the weight in water, divided by the weight in air minus the weight in the liquid. Furthermore, if a body of density sigma has an observed weight T when fully immersed in a liquid of density ρ, the buoyant force is ρ over sigma times the real weight W. This relationship gives us the formula. T equals W times the quantity, 1 minus ρ over sigma, which we can rearrange to solve for the real weight W in practice. We determine this by weighing the body in air as W1 and in the liquid as W2. The immersed volume V sub I is then equal to W1 minus W2, divided by the density of the liquid times gravity. This allows us to easily solve for either the body's density or its real weight. When does a body float? The next question is the simplest one. When does a body float? A body floats when its weight equals the weight of the liquid displaced by its immersed part. Let W be the body's weight and W be the buoyant force. Three possibilities cover every case. If W is greater than W, the body sinks all the way to the bottom. If W is less than W, the body floats with only part of its volume submerged. If W equals W, the body floats exactly at the surface with its whole volume just immersed. That is neutral equilibrium at the free surface. For the floating case, the immersed volume is Vn equals W over rho Lg. The fraction of the body's volume that sits below the surface is rho over sigma body density divided by liquid density. The fraction that pokes above the surface is V out over V equals 1 minus rho over sigma. Watch that ratio carefully. The denser the body, the larger the submerged fraction. Comparing floaters same liquid or same body. Two ways to read flotation are worth comparing. Take two bodies A and B floating in the same liquid, so the liquid's density sigma is fixed. Their immersed volumes scale with their densities, so rho sub A over rho sub B equals Vn sub A over Vn sub B. The denser body has to sink deeper to displace enough fluid to carry its weight. A piece of rubber sits lower in water than a piece of wood of the same weight, and that is why. Reverse the question. Float a single body in two different liquids with densities sigma sub A and sigma sub B. In the denser liquid, the body has to displace less volume to get the same buoyant force. So sigma sub A over sigma sub B equals Vn sub B over Vn sub A. A swimmer floats higher in the dense brine of the Dead Sea than in a freshwater pool. The body is unchanged. Only the buoyant force per liter displaced changes. Stability of a floating body. The metacentre floating bodies have a stability problem that simple buoyancy does not solve. The metacentre is the point where the line of action of the buoyant force meets the body's central vertical axis. The center of gravity of the body itself sits on that same axis, and where the metacentre sits relative to the center of gravity decides the kind of equilibrium. If the metacentre lies above the center of gravity, the body is in stable equilibrium. A small tilt produces a restoring couple that nudges the body back upright. If the metacentre lies below the center of gravity, the body is in unstable equilibrium, and a small tilt grows instead of recovering. If the metacentre coincides exactly with the center of gravity, the body is in neutral equilibrium, and any tilt leaves the body in equilibrium too. The practical rule is to keep the center of gravity low and the metacentre high. That is why ships carry heavy ballast at the bottom of the hull, and it is why a top-heavy kayak is much harder to keep upright than a low-profile canoe. Common trap and transfer point. There is one trap worth naming explicitly. The phrase heavier things sink is wrong as stated. A steel ship floats because its average density steel plus the air enclosed inside the hull is less than the density of water. What determines floating or sinking is the weight of displaced fluid, not the weight of the solid material. To pull everything together from this deck, the buoyant force is V rho g and it acts at the center of buoyancy. The force comes from the pressure difference between the bottom and the top of the immersed part, so the result is independent of the body's shape. Pascal's law is the rule that pressure transmits. Archimedes' principle is how that transmission shows up as a loss of weight. And flotation is the equality W equals W that decides whether the body stays up. Stability of the floating position is decided by where the metacentre sits relative to the center of gravity. Throughout all of this, we have been treating the densities as fixed numbers. The next deck asks what those densities actually are, how they combine when two liquids mix, and how they shift with pressure and temperature. Density and relative density, the single parameter that drove every formula so far. Pressure, buoyancy, flotation is density. Density of a substance is its mass divided by its volume, rho equals m over v. Its SI unit is kilogram per cubic meter. For a uniform isotropic substance, density is a scalar with no directional dependence, and its dimensions are ml to the minus 3. For reference, water has a density of 1 gram per cubic centimeter, which equals 10 to the 3 kilograms per cubic meter. Two practical identities are worth memorizing. For a solid body, the density of the body equals the density of the substance itself. For a hollow body, the density of the body is strictly less than the density of the substance, because the cavity adds volume without adding mass. Relative density, also called specific gravity, compares any substance to water at 4 degrees Celsius, the temperature at which water is densest. Relative density equals rho substance over rho water at 4 degrees, which in the lab is also the weight of the substance in air divided by its loss of weight in water. The ratio is dimensionless, it carries no units, and the second equality is the experimental identity. Weigh in air, weigh in water, divide. Mixing two liquids, the general formula mix two liquids, and the natural mistake is to average their densities. The right answer comes from the fact that volumes add when you pour them together. With masses m1 and m2 and densities ρ1 and ρ2, the density of the mixture is m1 plus m2 over m1 over ρ1 plus m2 over ρ2, which simplifies to ρ1 ρ2 times m1 plus m2 over m1 ρ2 plus m2 ρ1. Two clean special cases are worth memorizing. If the two liquids have the same mass m, the mixture density is 2 ρ1 ρ2 over ρ1 plus ρ2, the harmonic mean. If the two liquids have the same volume V, the mixture density is ρ1 plus ρ2 over 2, the arithmetic mean. Compare the two. The harmonic mean is always less than the arithmetic mean. So equal masses of two liquids give a mixture less dense than equal volumes of the same two liquids. The reason is that when masses are equal, the denser liquid contributes more volume, and that extra volume dilutes the mixture. Immiscible liquids and density changes with pressure. Drop two immiscible liquids into the same container and gravity separates them. The denser liquid sinks to the bottom and the less dense one rides on top, with a flat interface between the layers. That is why oil floats on water, and the pressure at any depth is then simply the sum of h rho g contributions from every layer above, a direct application of the hydrostatic equation from earlier. For a single liquid, density is not strictly constant. Under a pressure change delta P, the new density is ρ naught times 1 plus delta P over K, where ρ naught is the initial density and K is the bulk modulus of the liquid. The bulk modulus measures how hard the liquid resists being squeezed. For water, K is about 2.2 gigapascals, so fractional density changes from pressure are tiny under everyday conditions. For gases, K is much smaller, which is why atmospheric density drops noticeably as you climb. Temperature assumptions, and what the chapter quietly assumes. Temperature does the opposite. Warm a liquid and its density drops. The mass stays the same while the volume expands, so density decreases. With gamma the coefficient of volumetric expansion and delta T the temperature rise, the density becomes ρ naught over 1 plus gamma delta T, which for small temperature changes is well approximated by ρ naught times 1 minus gamma delta T. That linear approximation is accurate for the temperature shifts a lab beaker sees. And it is also why warm water sits on top of cold water in a glass until convection mixes them. Several assumptions are baked silently into this whole chapter, and they deserve to be made explicit. The fluid is treated as a continuous medium, so surface tension and capillary effects are off the table. The fluid is static in the pressure chapters and moving without acceleration in the buoyancy derivations. Temperature is assumed uniform unless the problem says otherwise. If it is not uniform, density has to be carried as a function of position. And atmospheric pressure is 1.013 times 10 to the 5 pascals, unless a problem specifies a different reference. Common traps and transferable takeaways. 5 traps catch students again and again. First, when you mix liquids, do not add their densities. Volumes add, not densities, so use the mixture formula. Second, do not forget the atmosphere. Total pressure is P sub A plus H rho G, not just H rho G. Third, do not treat gauge as absolute. Most gauges read above atmosphere, so absolute pressure equals gauge plus atmospheric. Fourth, do not say heavier objects sink, steel ships float because their average density is below water's. Fifth, do not assume same height means same weight. 3 vessels at the same height can hold very different weights of liquid while producing the same base pressure. The transferable takeaways go further. Pressure is the foundational equation of fluid statics. Every later fluid problem begins from P equals P0 plus rho g. H buoyancy is the same idea applied to a solid. Integrate pressure over the body's surface and you get V rho g upward. Pascal's law is the operator version of the pressure equation. Pressure transmits, volume responds. And density is mass per volume that changes with both pressure and temperature, so treat it as a function, not a constant, when those change. Outro for the Fiscribe audience. Hydrostatics is a single chapter, but it sets the language for the rest of fluid mechanics. Pressure is a scalar field. The free surface is the natural reference. Buoyancy is an integral over that field. Density is the parameter that ties mass to volume. 3 results are worth carrying forward into every problem you meet afterwards: the depth-only dependence of pressure, the displaced fluid definition of buoyancy, and the harmonic mean trick for mixtures of equal masses. These same ideas reappear in thermodynamics and oceanography and in any setting where fluids sit still. This lesson is part of the Physcribe YouTube channel, where we build short, calm, tough-style walkthroughs of physics theory, one chapter at a time. If this helped, subscribe to Physcribe and follow along as we move from fluids at rest to fluids in motion, then into waves and beyond. Two public references are good companions. The NCERT Physics Class 11 chapter on mechanical properties of fluids, and the Hyperphysics Fluids pages at Georgia State University, which have interactive diagrams of the hydrostatic paradox and Pascal's law.